Electron microscopy is a powerful tool for the study of bioscience and nanoscience. It has been used widely in industries as well. For instance, it is indispensable for the failure analysis of semiconductor devices and optical devices. The size of failures in such devices is so small that an electron microscope is the only way to analyze these failures. Not only in such advanced devices, electron microscopy is also indispensable in traditional technology, such as solder joining and plating. This is a schematic diagram of a typical solder joint and the corresponding electron micrograph. The solder alloy is a mixture of these black and white phases, which is called eutectic structure. Beneath the solder alloy is a substrate composed of electroless nickel plate. Enlarging this region, you can see a white layer at the interface between the substrate and the solder alloy. At a higher magnification, there are two types of void. One is round, and the other looks like bamboo lines. These voids must have been formed as a result of reaction between the solder alloy and the nickel substrate. Certainly, these voids weaken the strength of the solder bond. The micrograph can give us ideas on how to suppress the formation of such voids. Nowadays, people cannot stay without cell phones. Have you ever imagined that without solder joints, these devices would be of no use at all? Wiring in a device can be compared to a highway. This highway, in the nano world, exhibits various surprising phenomena, one of which is formation of whiskers. Whiskers give rise to a short circuit, leading to the breakdown of the device. This is an example of an aluminum whisker. The left side is viewed in bright field mode, while the right side is viewed in dark field mode. This whisker is single crystalline, although it is bent sharply, in the shape of the number 7. It has been believed that a whisker has the same orientation as the bottom crystal from which the whisker grows. Comprehensive analysis by electron microscopy reveals that the orientation of a whisker is quite different from that of the bottom crystal. This significantly contributes to our understanding of the mechanisms of whisker growth, and hence how to suppress it. Under tough driving conditions in a four-wheel drive, a wheel axis is subjected to a fretting fatigue, which is a kind of metal fatigue. This may lead to a disastrous breakdown in the wheel. This picture shows cracks at the cross-section of the axis formed as a result of metal fatigue. Magnifying this area, the crack looks like a river. Microstructure next to the river is quite different from the rest. This is the matrix. Diffraction pattern from the matrix shows that the matrix is definitely single crystalline, while diffraction pattern from the area next to the crack shows that it is composed of very fine polycrystals. Now you have seen that electron microscopy is widely used in industries. Why don't you consider using electron microscopes to improve performance and quality of your products or to develop new products? You may hesitate to do so because such devices are extremely expensive. On top of this, sample preparation is quite a task, and understanding of the data requires experience. Don't worry. Nagoya University has one of the greatest electron microscope laboratories in the world. Installed are 2 high-voltage electron microscopes and many others of highest quality. In this laboratory, top-level electron microscopists are performing cutting-edge researches. They will answer your questions. Let me introduce those microscopes that are open to your usage. The first and important step to electron microscopy is the preparation of specimens, in which the specimen must be thin enough for electron transparency. Even a cooking foil made of aluminum is far too thick for electron microscopy. But you have nothing to worry about. Experts at specimen preparation will create the specimens for you. Here, are the different types of machines for specimen preparation. Depending on the substances and purposes, the best machine will be chosen. Now that your specimen is made ready for observation, let me proudly introduce Nagoya University's collection of electron microscopes. The first microscope is the high-voltage electron microscope. Its accelerating voltage reaches 1 million volts and higher. Thanks to this high accelerating voltage, specimens much thicker than those observable with conventional 200 or 300 kilovolt microscopes can be examined. The fact that thicker samples can be used makes it much easier to prepare good specimens. This is an optical micrograph of an etch pit formed on the surface of silicon carbide crystal. If properly etched with a chemical reagent, an etch pit like this is formed on that point of the crystal surface where an internal defect, known as dislocation, emerges. However, the dislocation itself inside the crystal cannot be observed with the etch pit method. An electron microscope is necessary to analyze the morphology and nature of the dislocation. The problem here is how to prepare a good specimen. A good specimen in this case means one containing the target dislocation. With conventional electron microscopes, the specimens must be as thin as 200 or 300 nanometers. You can easily imagine how difficult and tedious it is to enclose the dislocation into such thin specimen. The situation is much easier when a high-voltage electron microscope is used. With the high-voltage electron microscope, specimen with thickness of 1000 nanometers is observable, which makes specimen preparation so much easier. This is an electron micrograph of a dislocation, observed by the high-voltage electron microscope. The etch pit is formed exactly at the emergency point of the dislocation. This is another micrograph taken from the same dislocation as in the previous image, but with a different diffraction condition. You can see that the dislocation has disappeared. This is the so-called contrast experiment, by which the nature of the dislocation is determined. Furthermore, if observed with the weak beam method, a method of high resolution, the dislocation, which appeared as a single line at a lower magnification, now appears in a pair. Such information is extremely useful to determine the nature of a dislocation in silicon carbide, without any ambiguity. The important point about this particular microscope is that it is the only high-voltage electron microscope in the world in which high-resolution weak beam method can be applied. Let me introduce another example that observes thick samples easily. Let's go back to the solder joint. It is of course useful enough to observe solder joints by electron microscopy. However, wouldn't it be more interesting to be able to observe the soldering process itself, at high magnification, and at real time? When asked this request, specialists in electron microscopy would normally claim that it is absolutely impossible since solder joints contain liquid metal. Nagoya University is an exceptional group that is able to challenge this issue. But how? As mentioned several times, specimen must be very thin. As soon as it is melted, it becomes round and thick due to surface tension, eventually being too thick of a specimen for electron microscopy. One way to prevent this is to cover the specimen totally with a strong film such as carbon. If the carbon film is too thin, it cannot keep the shape of thin liquid foil after melting. To the contrary, if it is too thick, the electron microscopic image will be blurred due to the absorption of electrons by the thick carbon film. So, we face the dilemma of choosing either thicker carbon film for shape maintenance or thinner carbon film for high-quality image. Now is when the high-voltage electron microscope exerts its ultimate advantage. This video shows real-time observation of solder joining process. Needless to say, this is the first observation in the world. The area above the line is the solder alloy. At room temperature, the solder is in solid form. A few reactions have already taken place at the interface between the solid solder and the nickel substrate. Let's observe what happens when the sample is heated inside the high-voltage electron microscope. The solder alloy is still solid. Now, it melts. The liquid here has a very uniform contrast. All of a sudden, the interface becomes busy. Large columnar crystals are formed one after another. Thickness in the white area increases as well. This is the real process of solder joining, observed in the nano world. Another technically important process which involves liquid metals is zinc plating. You may think that zinc plating is low-tech. However, this is not the case. Zinc-plated steel, or galvanized annealed steel, is the most expensive and high-performance steel, and it is used widely in automotive industry all over the world. Is it possible to observe reactions between steel and molten zinc? If zinc is heated to melt in vacuum, it will evaporate violently because of its high vapor pressure. So, it is by far much more difficult to observe reactions between steel and molten zinc than to observe soldering process. Let's start this unusual experiment. Zinc is still in solid state, showing some of its individual crystal grains. Now, zinc melts. Reactions are taking place violently at the interface, and reaction products are formed, layering after another. This experiment that observes reactions between steel and molten zinc is also the first in the world to be carried out. Next is the 3D electron microscope. During CT scan in a hospital, the patient enters a tunnel of X-ray source. The X-ray source rotates around the patient, producing tomography. In the case of the electron microscope, the electron source, which is the electron gun, is fixed. So, the specimen rotates instead. A 3D image can be reconstructed, and the internal structure can be visualized three-dimensionally. You can feel as if you are actually entering the nano world. Another important feature of this microscope is its ability of observing and analyzing at very low temperatures, such as those of liquid nitrogen or liquid helium. Unfortunately, some samples fade during observation due to electron bombardment. Polymer material is a typical example of this. This series of diffraction patterns shows how polymer changes its structure from being crystalline to amorphous during electron microscopic observation. At the very beginning of the observation, the debris rings are clear, but they fade away as it continues. This experiment was carried out at liquid helium temperature. During the beginning 30 seconds, the sample appears to be all right. This graph shows the comparison of crystalline disappearance in liquid nitrogen temperature and in liquid helium temperature. At liquid nitrogen temperature, crystallinity in one of the samples is destroyed in an instant. However, at liquid helium temperature, its rate of change is much slower. You may realize now that observations in extremely low temperatures can be very useful. The next microscope is a dedicated in situ microscope. It is equipped with a special specimen heating holder, which is able to heat a specimen at temperatures as high as 2000 degrees Celsius. A fine, tungsten wire is used as a heating element which is heated by direct electric current. The samples are mounted directly onto it. In this case, alumina ceramic is melted at a very high temperature of nearly 2000 Kelvin. The spherical parts are in liquid form, while the stems are made of alumina crystals. At a higher magnification, crystal lattices can be observed inside the solid, but not in the liquid. Therefore, this is the interface between the solid and alumina liquid. Many people believe that observation of a liquid through an electron microscope is impossible. However, this micrograph proves that this assumption is definitely not true. The dynamic behavior of the solid-liquid interface can be observed. The alumina molecules are dancing around, as if alive, at the solid-liquid interface. You can recognize that the crystal is moving downwards. If two heating elements are used, much more complicated phenomena can be observed. For instance, let's try placing bismuth metal particles on top of heating element 1, and spherical particles of silica ceramic on heating element 2. First, bismuth particles are heated and evaporated. Then they are sprinkled onto the surface of silica substrate on heating element 2. The smooth silica surface, covered with droplets of liquid bismuth, becomes rough. Heating element 2 is now at room temperature. Therefore the bismuth particles are crystalline, as their shapes indicate. Bismuth melts when heating element 2 is heated in temperatures higher than its melting point. It becomes perfectly spherical, like water droplets. You can induce gas to the sample and observe reactions between gas and liquid, or reactions between gas and solid. This shows a process of which a liquid tin particle reacts with oxygen to form an oxide layer. Before the oxide layer is formed, liquid tin is perfectly spherical. During oxidation, it becomes faceted due to the crystallinity of the oxide layer covering its surface. Under some conditions, the oxide may form preferentially at the interface between the silica substrate and liquid tin. The oxide lifts the liquid tin, building a whisker. This is a field emission electron microscope. It is especially useful for observing magnetic materials. A conventional microscope cannot escape the effects of the magnetic field in its objective lens. However, this microscope is equipped with a special lens, which makes it possible to observe without being influenced by any magnetic field. The left micrograph shows a barium ferrite particle, observed in conventional bright field mode, while the right one shows the same image in holography. You can see that the north and south poles are connected with magnetic lines. In addition to these microscopes, Nagoya University has many others with high performance. If you are unsure of which suitable microscope to use for your project, the coordinator, who is an expert in electron microscopy and material science, will be there to give advice. You must be wondering how much it will cost to use these electron microscopes, and how security is conducted in the facility. Regarding security, there is absolutely no problem. Only dedicated researchers are involved. Students and postdoc students are not. Please visit our website for further details. If you have any questions or comments, feel free to contact us. You are most welcome.